When it works here. Hello, YouTube. Hey, it's Bill and Ben show, except that Ben can't be with us today. I've got somebody else here that you may know from our Discord channel, Mike Fikes, who you and me just recently met in the last year. Has it been maybe a year already?
It was like, it feels like it was in the winter last year.
Yeah. And basically, you approached me to help with some design. What can you...
Yeah, at the time, I was like, we were doing some stuff at work, and we were building some stuff with Raspberry Pis, and we wanted to do a demo for a customer, and we were trying to figure out ways to, like, make that Raspberry Pi be more robust so it wouldn't crash or, just electrically fall apart. And I built some stuff on a breadboard with an LED. And one of the demos we gave, we got some feedback like, yeah, that's not good enough. You need to actually go. And like, we were working on unlocking cars, and we were using an LED to like show how our software was working. And to be honest, at that time, I had just learned the whole thing that you need to put a resistor with an LED, right? That's how little I knew about this stuff.
Right.
I was like, I just thought you plug it in and it goes. So we were doing some stuff with basically ODB. To try to unlock cars that way. Like we're like, oh, here's our challenge. Go and unlock a real car. So I had just happened to remember like, oh, I saw some videos where Bill was doing some stuff with his truck with ODB. And I was joking with one of my boss, and I'm like, hey, we should just contact Bill to see if he's interested in helping us build something that would, help us like make something that's more compelling, Right. And, oh man, that's like turning on the floodgates when you start working with Bill.
Well, I think the first thing it's interesting you mentioned the Raspberry Pi. I'd kind of forgotten about that, but I think the very first conversation we had, not very first, but one of the early concepts was the difference between a computer and a microprocessor and a microcontroller. And we ended up in the ESP32 line just for grins.
Yes, that was the first time I had ever even experienced the whole microcontroller thing. I had never done the Arduino thing or whatever, and the thing that was shocking to me was how fast the thing pops up and goes. Like you just turn it on and it's running.
Right. Like, and whenever I see a Raspberry Pi, what I see is, it takes a while to boot, and then what I'm crazy about is that the flash file system can be corrupted by things like bad shutdowns. Well, a controller's life is bad shutdowns, right? It's you don't know when the power is going to be removed.
Yeah, that was one thing I was worried about, was like, we were even considering, there's these industrial enclosures that you can put around a Raspberry Pi to like take care of some of that stuff, like to make sure that it, like if you unplug it, I think it keeps a battery in there and keeps it going so it can shut itself
for
down.
A minute, right?
Yeah. All that kind of stuff. Yeah, we were really worried, like we were going to ship some demo hardware to a customer and they were going to get it, and we were afraid that it was going to fall apart. And, and we didn't know hardly anything about this stuff other than like, it's basically we knew software and how to develop for a Raspberry Pi, but we didn't know how to keep this thing up and going. And then Bill, you basically mentioned ESP32, so that was the chip I think you found that had like almost all these things in it, like Bluetooth, CAN, the works was in this one module chip or whatever.
Right. Yeah. There's kind of an art to finding the, all the different features and finding what handles all those features. But then right off the bat, you got a lesson in, we both had to go through the pinouts of all the various functions, because in one function, this pin does one thing, and in another function, it does another thing. And we had to make a printed circuit board use the right pins, quite frankly. And you remember reading those data sheets and going, it's a near field pin in this mode, and it's not a CAN mode, a CAN pin in this mode. But the ESP32 worked for us. It booted fast. It's got two processors in there, and so that was a reasonable first prototyping aid. We've since moved on to Nordic.
Yes, yeah. And along the way, we went through TI, CC2640 TI chips. So it's like you said,
that's right.
Every time you meet a new chip, it's like they all are different in their own weird, perverse ways, right? You have to learn, like, how do you, like, I don't know what you call it, but maybe it's called the bring up, the first time you can boot the thing and get it.
Oh, that's the hardest part. It's either the light bulb comes on or not, and that's the whole thing is, can you get it to boot? Then you can fix it. if it boots. So,
And that's always
okay, we have people asking, who is Mike? Mike is, so Ben couldn't be with us today. He's driving, and he offered to call in while driving. And the last thing I wanted to do was hear a car accident while he's driving. And so we said, well, let's just have somebody we know and has been part of the Discord group since the beginning. So, and my friend here, Mike, is joined us for the day, and he's got a lot of cool stuff to show us. So that's one of the things we're doing.
I can't fill Bill or Ben's shoes, but I have some stuff I could show you. I have some cool gear to show.
So, well, talk about yourself a little bit. You've met the astronauts, right?
Oh yeah. When I was a kid, I was born like right when the Apollo stuff was happening, but I was too young to remember it. Right.
And I saw it on TV. Yeah.
So when I think about me and what influenced me when I was growing up as a kid in the 70s, it was a couple of things. It was the fact that we had just sent this gigantic rocket to the moon. You can't ignore that as when you're a kid, as an engineer.
Right,
like, oh man.
Right.
And another thing was, oh my God, there's these computers you can now buy and have in your home, and you flip them on and they run BASIC, right? So those were two things that just blew my mind, right? So for me, I ultimately wanted to be an aerospace engineer, and I ended up being taught by the same teacher that taught Buzz Aldrin and a couple of the other Apollo astronauts. So I followed that dream basically, and I never did anything with it afterwards. But I learned, and got to satisfy that thirst of mine, which was to hang out with some of the people at Draper who built the early Apollo software and stuff like that.
Right.
These things can influence you when you're a kid,
That software was amazing. That did ran the lunar module and ran the service module, and I remember them going, it's good enough you could do the navigation from the onboard computer, and yet there was enough distrust that they would still do the calculations on the ground and uplink them. But the computer on board could have, in a pinch, figured out how to land on, the where it is exactly in relation to landing on the moon.
Yeah, the thing that still always amazes me about that is you have to try to put yourself back in that point in history and remember how little technology there was. And like one small example of that is like when the astronauts would leave the spacecraft and go out and walk around and come back, they had a certain amount of time, right? Like the backpack could last for maybe like 15 minutes or whatever time limit it had. And they had to time that, right? Because they wanted to, they had to say, hey, Neil, come back to the spacecraft, you're running out. So what they did back then was, I would imagine in my mind, it's like, they would use like some special timer, whatnot. But you look and you see like they have wind-up watches back then, wind them up. And
right.
They didn't have digital watches, or maybe they were just now coming out. It's like that makes it even more amazing when you think about what they pulled off with how little they had back then.
I remember looking as a kid. We were at, I guess it was the Gus Grissom Museum in Ohio, one of those places, and you can go up the steps and look in probably what was a Mercury capsule looking back, and you can see behind the control panel through the plexiglass, and it looks like a pinball machine. It's just relays and wires. There's no computer modules, anything like that. It was latching stepper relays and it was amazing it flew, but that's how the airplanes flew back then.
And that reminds me, I was just watching, there's a show I was watching that was recorded in like the 50s, and it showed how TV sets were made back then. And it reminded me of you, Bill, because that's how you started, right?
I have old TVs.
And I was looking at that stuff, and it was like they were like going through the process of designing basically what would be like kind of like what is today a PC board, but it was like, a thing to hold the components on it. And they had like the wave soldering or whatever they're doing back then. And what struck me was like all the notions that we think about today kind of existed back then. Even like EMC, they like got to a point where they were talking about, they weren't calling it EMC in this video, but they said they know that TVs can interfere with other TVs. So they go out and they measure them and, make sure that they're not radiating emissions that would bother someone else. And it was just like, wow, all this stuff was actually all existed back then. It was more crude, but all the ideas were there.
Right. Somebody just asked, weren't the early spaceships DTL, diode transistor logic? Can't read the rest without my glasses, but I'm sure they grew into it. I just remember as a kid seeing all the wires and going, oh, this is not at all what I expected, even as like a 7-year-old kid looking in and that was again probably one of the Mercury capsules, Mercury or Gemini is one of the real early ones I saw.
But there was like some, I can't remember the details of the history, but like the whole NASA stuff really kind of caused the whole IC industry to kind of, they were like a reason to buy a lot of ICs or transistors. And
Texas Instruments, yeah, I've heard that. You know, the Russians, or we got somebody to take a look inside of one of the Russian ICBM missiles or something, and they said they saw the eyes of Texas in there. In other words, they had to buy our chips for their missiles because they didn't have that kind of capability back then to make the kind of chips, and they didn't have hand calculators. They used pencils.
Yeah.
The cosmonauts did. So, yeah, somebody mentioned Wes just mentioned Fran Blanche talking about this on an old Dino Den show that me and Fran had done years ago. And she really knows her way around the lunar, disky, you know, yeah.
All that stuff. If you, for the audience, if you don't know, what DISCI stands for, what? Display and keyboard. It was the little thing that Michael Collins would type the commands into to get the spacecraft. It was the way to interact with the computer back then, right? It was your interface to the computer. That's what DISCI, it stands for something like, I think display, keyboard, something or other. Something like that.
Yeah. Somebody look up DISCI and post it in the YouTube chat channel.
Maybe? Yeah.
Yeah. So, yeah. So since meeting you, you've gone on a kind of I don't want to say a bender, but you've accumulated an awful lot of RF gear in a very short period of time.
Yeah. So I thought of this. For me, it started off being kind of like a hobby. I got into I got sucked into it by the whole bin eater stuff and making your own breadboard computer. And I was a software developer, so I was easily sucked in from that side, like, oh, how do computers work? And for me, it was a hobby for quite a while. And when it's a hobby, you're only willing to spend so much money to buy gear. And then it started to become important to me for work. I'm like, I got to do this for, it was like, I have stuff I have to get done for work. So I could more easily justify buying things, when work is on the line. Yeah.
And I simply wouldn't tell my wife what I was buying.
Oh, you have to, you just have to spread it out over time. Yeah.
Yeah. Yeah. But so one of the things I see sitting right behind you is a TEM cell. You want to tell us a little bit about that and why you got that?
So, like I mentioned with the TV story, you have to worry about interference. So when there's the whole FCC, and in Europe there's an equivalent organization, and you need to, when you're going to release a product into the market, you need to satisfy certain regulations and rules to make sure that your product is not causing interference. And the TEM cell.
I remember you made a comment when I sent you a good FCC summary, and you said, I never realized FCC was more about not interfering with your neighbor's computers than your own.
Yeah.
And that's absolutely correct.
Yeah, I had always kind of built this mental model that the FCC was there to kind of protect the consumer from buying basically just bad electronic products that would interfere with each other and just make a mess of things. And really, that's not the FCC's bailiwick, I guess. They're not there to keep you from harming yourself. They were there to, you can't harm your neighbor, really. That's what it's really all about at the bottom in terms of regulations. So here's
somebody's saying, what's that giant box that says Tektronix, Bill?
That's a oscilloscope. It's an old oscilloscope behind me. Yeah.
I don't know if they mean behind me or if they're seeing my big Cisco router sitting on a bench behind me. So, but show us the TEM. Yeah, hold that up.
This is a TEM cell, and the way I think about it. Let's see if I can. All right, over here. The way I think about this thing is it's basically a transmission line that's been split open. I mean,
yes, it's a coax that's torn open. Yes.
Yeah, it's like the impedance of this coaxial coming into it is 50 ohms, but then if I hold it up this way, it spreads out in such a way to keep the whole thing 50 ohms, and this thing in the middle is. All right, the right term for that is what, strip line?
It's a strip line. It's a 50 ohm strip line, and yet inside, I believe that the impedance in the free air is still 377 ohms.
Okay.
For the transference to, but don't quote me on that. That Ben would know better.
And we think the TEM stands for transverse electromagnetic, and is related to the TEM mode, and we think it's an even transmission of stuff through this.
Right.
I was recently reading about I didn't know this coaxial cable, and I don't know if this is exactly related, but coaxial cable, when you're shooting signals through it, is evidently in the TEM mode, but then that only works up to a certain frequency, and then if you go above that, you get into this T11 mode, and that's just at the edge of what I'm learning about. It's like all these weird, like, instead of the things oscillating in a weird way, they start to bounce up and down inside the cable in a weird
or circular or
yeah. So the idea here is that you can put something inside of this because it's so big. Well, this one's not that huge, but it's big enough to put, like the products we're working on are about this size. You could fit it in there. And then if you do that, if this thing is radiating at all, like if it's spitting out any EM stuff, you'll pick it up, basically.
Right. And you can do the opposite. You can hook a signal generator to it and put something in there to see if it's susceptible to.
Yeah, you would put like a big honking amplifier on there and try to like, and I did that. I actually got like some 7500 logic thing that I had built, and I put it in there and I was like driving it really hard, right? And you could measure the signals, and it makes you appreciate how good some of the noise margins are on some of that stuff, because you can see the stuff bouncing all over the place, but it's still working. You know, it's holding itself together, and this thing that I built was like a counter. You know, it was counting up, and it still kept counting, even though it was like a noisy count.
Yeah, and so in EMC, you know, going back, one of our rules of thumb was that something that is susceptible also can radiate. So we used to use susceptibility. We used to take walkie-talkies, things like that, pass it around the product, and if we can cause the processor to reset, we know we got a problem. And we know we'd have a problem with radiation as well. If you could get that much signal into it, the signal could come back out.
Oh, it's like the symmetry, right? Like if it can, like you kind of pointed this out.
An aperture is an aperture, yeah.
An antenna is good for both sending and receiving. Yeah.
Yeah. So they're talking about scopes, and I was going to bring mine out, but it's too wired in right now. But I have a MDO. I have an MDO 3104 in my lab back there, and that's a real nice scope from. Yeah, it's a real nice. Thanks to Tektronix for that. So what are you showing us here? That looks like a spectrum analyzer.
So it is a spectrum analyzer view. It's a little bit off screen, you can't see it, but it is basically the signal coming out of this TEM cell. And I threw this device in there. This is actually a device that Bill had designed the board for, and it's in there. And now that I pulled it out, you can see that it's starting to flatline. The refresh rate on this is pretty low because I put the spectrum analyzer into like a 9 kilohertz bandwidth mode. Yeah. It's it takes a long time to get across. So when I put this device in there, I'm actually putting it back in the kind of the bottom of the septum, or whatever they call that, the bottom half.
Yeah,
of it.
It's a septum. Yeah.
And it's now picking up the. I want to say that those spikes that you're seeing are due to, if I remember correctly, there's a switching regulator inside this device.
Which we started with and then went away from. We started with the switching regulator because we didn't know what the current draw would be. So we went with something that wouldn't be a problem for the first versions.
Yeah.
And then once you got dynamic power, we said, oh, let's go with the linear regulator. And it got a little nicer then.
Yeah, so I could actually throw one of those in there. So this is, it's probably not that fair of a comparison because this one's got we were using metal enclosures back then. And this other one had a plastic enclosure, but I'll throw it in there. And you'll see that there's a big difference in the radiated emissions for this guy. And
so,
yep, go ahead.
I was going to say, and one of the reasons we use a TEM cell for radiated emissions is you can get more consistent results than if you use your near field probe, which is another way to measure. But and you have near field probes. Maybe you can pull one out here in a bit.
Okay. So near field probes
afterwards.
Here's so actually this is you can now see. I'm sorry if we go back. This revised device in there looks like it's got a few spikes, but they're much lower now. Perhaps due to other things.
They're like 80 dB down too, aren't they?
And the to be honest, like what's interesting is you can, like Bill was pointing out, you cannot use the TEM cell to see if you will pass FCC or not, because it's just a relative thing. You can like see, do A/B comparisons. And if you do have noise, and this is how I actually found out that it was the linear, or that it was a switching regulator, is you use these, this is the okay, let's see if I can name this. This is the near field probes that you can also hook up to your spectrum analyzer, and they will let you probe around on your board to get more kind of like specific locations on your board that are radiating. So for me, I took one of these and I put it near that, that regulator, and I could see that it was the thing that was causing those spikes.
Right.
It helps you identify which thing is causing the noise.
Well, it allows you to localize it. What's interesting is 3 of those probes you showed are for the magnetic radiation, and it's only the smallest one at the bottom that is for the E, if that's correct.
So this one here is a magnetic one, like Bill says, H field probe, and then they get smaller and smaller circles, and then at the very bottom is one that is
it's just kind of a sense. It's just kind of a tip.
Yeah. And that one, to be honest, that one's less, or for me so far, has been less useful. Like the H field probes seem to like pick up more stuff, but I know both of those are important, I guess. Maybe
right.
Maybe it's more common to have magnetic problems in your boards than.
Well, where you have noise in one, in the magnetic field, chances are you have noise in the E field also, and vice versa.
So one thing I wanted to mention about all this stuff, and I have some more gear to show, which I think gets into like you might have in your mind, like, can I test whether or not my stuff is going to pass FCC or not? Can I take some absolute measurement rather than a relative one? So the TIM cell is just for like A/B comparisons, and it's very consistent, like Bill said. You can like see, did you improve something? And the H field probes kind of like lets you know on the board where the thing is, but it won't tell you whether or not you're going to pass a test or not. So there's a couple of things I have. One is an antenna that has been calibrated, I guess, or whatever.
Calibrated, right.
Oh man, this one's big. This is another box from TechBox. I like this company. They make lots of EMC gear. And this, let me open it up and show you what it is. It's a biconical antenna.
Right.
And it's just like a wideband antenna. And the main thing about it for FCC stuff is that it comes with a calibration chart that tells you, like if you put your device under test maybe like 3 meters away, it'll tell you that that translates into certain units of strength, field strength. And then you can like back that out and see whether or not you're in compliance with certain regulations and whatnot.
Right. The field strength ends up to be in microvolts, basically. Here's part of my biconical. This doesn't have the frequency range of yours, but it's got more surface area. It probably has more pickup. But again, it'd be useless if I didn't keep the manual that tells me the antenna factor at each different frequency, which is that conversion between the radiated field and voltage, basically. Voltage into a load.
And one thing I've found with this thing is that
this is cute.
Yeah. It's
one of the things you found is what?
Oh, so if you hook this up to your spectrum analyzer, it's kind of hard to just see stuff. Like it's like the signals are kind of a bit weak or whatever. You can put an amplifier on it, but evidently the way you're supposed to use these things, and I don't have a whole lot of experience with this stuff. I'm just kind of like learning it. But evidently what you're supposed to do is use the TIM cell to kind of point out to you where your spikes are. It'll say like, I have a spurious spike here at this certain frequency. Then you take this guy and you zoom in on that particular frequency and you see what its strength is at that particular frequency. Like, so that's all I wanted to say is like, it's hard to see, like if you just plug this in, it's hard to look for problems because you just see a big mess of stuff and it's all kind of weak.
Well, and that's the problem with doing it in the lab is you're going to see the background and you can try and subtract out the background.
Yeah.
We used to do that in FCC testing. I was within a couple dB when I would go to the lab. And sometimes all I'm doing is turning it on and off, the piece of the device under test, and would see that when the spikes grew and when they stopped, that spike was due to the equipment under test. But but with that said, I had a quiet place in the warehouse where I had one of my antennas set up a certain distance. I had my antenna factor chart, and I had a spectrum analyzer like you've got. And by just being meticulous, I was able to scan the full spectrum and be within a couple dB of absolute.
Yeah.
So it's that antenna factor book in my book that makes it.
And even like the resolution bandwidths you choose become important and stuff like that. You don't want to just like hit your thing on preset and let it go. You kind of have to like, there's a lot of things you have to follow to get these things measured properly.
Now TechBox has software that does. Yeah. Do you remember reading much about that?
Yeah,
because it did what you're saying.
And the software, I think, is available for some of the newer, like the Rigel or Siglent gear. Yeah. I have an old ancient, you can't see it, it's an old HP spectrum analyzer that's built like a tank from the 80s or whatever.
Yeah.
It didn't know what software was back then.
Nah. But the software, will actually set up your spectrum analyzer to use the right bandwidth, the right sweep rate, all those things. And I have that software. I have a demo copy of that for Tektronix. I have a Tektronix spectrum analyzer, and it does all the work for you. You punch in antenna factors and everything, and then your final readout, it'll actually superimpose the FCC limits, and you can look and see if you pass or not. And if you punched your numbers in correctly, you should be within a couple dB of that.
Yeah, and I understand what I have to do without the software is I have to pick the right bandwidth, and then you can't cover the whole range with that because you just can't. You have to start off at a certain lower frequency range, measure that part, and then go to the next chunk. You have to kind of split and divide and conquer and basically do what the software would have done for you. Yeah.
Right. So what else you got?
So we so far have been talking about radiated emissions, right? In terms of like electromagnetic radiation, but there's also conducted emissions that you have to worry about. And I think that's largely because conducted emissions can easily cause radiated emissions, or you just don't want to put noise into the power circuitry.
No, you hit it on the head. Is conducted emissions just turns your power cord or your joystick cable into a big antenna if you're not careful.
And it's evidently real easy to do, right? Like a small amount of current, a common mode current maybe, can really easily cause a problem.
If you have current flow, there's a saying I have, which is where there's no current flow, there's no field. So one of the things, when shielded cable is a rule of thumb, your mileage may vary, but you don't ground both ends of a shielded cable because then current could flow and it's no longer a shield, it's a radiator. So a typical thing we do is we ground it usually at the piece of equipment we're trying to protect, and it's grounded only on one end and acts as a shield. There's another point of view, though, that a magnetic shield doesn't work unless there's a continuous loop. So, there's some art in that.
Yeah, I recently, one way I kind of visualized it was I was watching a Rick Hartley thing, and he was kind of explaining that the shield on the cable is really meant to just be thought of as like an extension to the Faraday cage that the enclosure made.
That's right. And you don't want current flowing in it.
The 360 soldering or connect it really well to make it truly be a Faraday cage. Okay, so here's the next
another box.
Another tech box.
Yeah.
And this one is a current probe. Hello there.
Yep.
So the idea here is you pass a cable through it and hook it up to your SA as well, your spectrum analyzer. And from that, you can see a spectrum that's, it's basically induced, I guess, as the currents go in and out of this thing. And this also comes with a chart or whatever, a calibration thing that tells you that for this particular amount of, I guess you change units on your spectrum analyzer. Normally you're looking at dB, right? Or dB of...
dB per microvolt, something like that.
Yeah. And on my spectrum analyzer, you can punch in some things to tell it to show different units. And then things run like negative, like 0 dBm is 1 milliwatt, and then you're going down, usually negative, right? Typically. Right. And in this other scale, it tends to go up for whatever reason. You're going from 0 up to 80 or more. It's just a different set of units, really. But that's one thing that I think can get you closer to like an absolute measurement. I want to say like this is not like a relative thing so much because of the fact that it's calibrated. You can say this will tell you something specific. And then the granddaddy of all that stuff is the Listen stuff. This is another, I think, is probably the better way to measure conducted emissions. Here is a Listen.
Right, and that's a listen not for that's a listen for not power but for I/O cables and things, right?
I use it for power.
Or you could use it for 12-volt power. You wouldn't use it for 110.
Yeah, this is a DC Listen. Actually, what I'm holding is a Listen Mate. Let's see. Let's see if I can show this. I have these things sitting on. Yeah, here they are. I can grab them. So I have here's an actual Listen.
Right.
They look. The other thing that I was showing look roughly the same. But what it is you can buy two of them. Why not? Like if you have one, you could buy another. And what you can then do is you can hook this thing to that other thing, the Listen Mate, and you can separate out the differential and common mode.
In common mode, yeah.
Yeah. So, and all this stuff. This was a good piece of advice from Bill. Let's see. Useful. A big piece of
ground
steel,
plane.
A ground plane. To put all that, we'll vouch for that. It's like if you just put it on your bench and you start measuring things without, there's a proper way to hook this stuff up so that it's like above this ground plane, and it effectively, I want to say, makes your measurements less noisy, and you see things that are close instead of picking up garbage from your environment. Like I live near an airport. I live near Dulles Airport, and there's all.
I love you too. Your emissions.
Anything that I.
Yeah. Well, you and me made something that uses emissions on intentionally shove in a box. We had Bluetooth, near field.
Oh,
that's it.
So, Bill, someone is saying that the stream went down. The YouTube stream.
Yeah, it says just lost you. Somebody said that there too. So there, I think it's back.
Okay.
And that's not me.
Okay.
I've got really good connectivity, folks.
Okay, people were saying that it came back.
Yeah.
So going back to what you were saying, Bill, is we had like
went down again.
Yeah.
And it's back up.
So one of these devices. Okay, so inside of one of these little devices here, I wish I had one open to show you, but it has like a Bluetooth radio. The old ESP32s can do Wi-Fi, which is effectively the same spectrum area, right?
Spectrum, right.
A UWB antenna is ultra wideband, and it's good.
That's the one I forgot.
Yeah, you were rattling off the other ones. Let's see. Oh man, we threw everything cellular. But it's like you have like.
I thought we did with cellular.
Yes, right, we do. We have one of those too. But you run into this problem where you have like 5 different antennas, all device, and they're all competing.
Interfering, and that was from the beginning, as you know, that was my whole thing, is I don't want to build a big OS or a big interference GAN. But basically, you made a time where we're about 2 radios on at once.
Yes. Yeah, and even if you're like using it uses the actual same antenna for both BLE and Wi-Fi. It will like between the two.
That's right.
Yeah.
Right.
Stream
so
back
people are watching it on back. I wrote very little of the software, and so I don't know how to fix it, unfortunately. It's not my so the only thing we could do is any 2 connectors, make a high quality,
like see the effect.
Yep. And everybody's like, oh, don't use square corners. Well, yeah, they're behind why not to use a square, but on regular stuff, you really won't notice a square corner. It goes, what I'm talking about is in a trace, whether you bevel the traces. A square corner ends up looking like a straight wave with a triangle glued to it, from the corner of the trace. And so it's that change causes a change of capacitance. But what I showed is it goes by the thing so quick that it didn't show up even at 20 gigahertz very much. But what was far worse were VIAs. VIAs were just horrible at some of these high frequencies. They bounce stuff off the barrel. They act like antennas if they're going all the way through the board, but you're only going to the second layer. So yeah, there's a Hackaday article on that called Debunking High-Speed Myths.
The meta notion to me is this whole thing where sometimes it's difficult to get at the truth of what's really going on, especially like back in the 70s and 80s when you didn't even have the gear that could measure some of this stuff. So a lot of myths would crop up and people would start to come up with these beliefs that they had on what was really going on and these rules of thumb. And
right.
And I guess it also goes along with like I don't know if this is Lee Ritchie or one of these people say, like, don't say something unless you can prove that it's actually true, because you're just adding to the confusion, you know?
Right.
I mean,
Well, and I love what he says. He often will just say, how do you know? And somebody posted something to the SI board that said, oh, I have a FR4, 4 material. And he's like, what material is exactly 4? And he's right. It's 3.9, it's 4.2, it's something like that.
And all this stuff is knowable, but you have to at least be honest with yourself for the parts that you don't know, the things that you haven't measured, and they're just like, is that just something that I were, kind of latched onto? Do I really?
And the danger is, let's see what's happening. So I want to stop doing something and risk failing, So we would do a certain way on the edges. Well, nobody wanted to be the person and have it fail. So we would perpetuate these rules of thumb because nobody wants to be the guinea pig. Or worse yet, it fails and you don't things you did cause we didn't have those kind of instruments.
You're supposed to do if you can't pay the price.
You get a feel for it.